recently I got a DM about hydroboration-oxidation and some help with the mechanism. So today we're going to learn about that and go through the mechanism. So hydroboration-oxidation, bit of a mouthful, is a way of taking an alkene like you see here and making an alcohol using some sort of borane species, a base, and then a peroxide. And what's special about it is it's regiospecific in that it only leads to anti-Markovnikov addition, if that's a possibility. And then it's stereospecific in that you get syn addition in the H and the OH. There's no stereochemistry here. But if there was, they would be on the same face, same side, adds from the same side, syn. All right, so let's go through that mechanism. We have our alkene here, or BH3. And the way it's going to add is, where's my pen? Here we go. I'm going to do kind of like dashed lines. This is going to come up and grab this. And then this kind of goes here. But what it leads is you get a kind of a weird transition state. And this is why the boron adds in the least substituted position, is you have H here, your BH2, and you have a transition state that looks like this. And that's because one, the boron is just simply bulkier than the hydrogen, so it's going to add at the less hindered spot. Also, even in, say, an example like this, because this isn't really a hindered spot, but there is a partial positive charge that forms here during this transition state. And while it's not a full carbocation, similar to a carbocation, it is more stable over here on the secondary carbon. So that's why it forms there, and our boron adds here. So what we are left with then is, after this step, this is a two-step mechanism. We have a trialkyl borane, and we have BH2 here, and we have our H here. Now, there is no stereochemistry on this, but like I've said, this is syn addition. So see how this adds from the same face? So it's syn, same. It's just, think of it as it gets pushed on down there. So if we were to assign it any sort of stereochemistry, we'll give it a wedge. They'd both be on a wedge because they came from the same face. Then we actually have to oxidize this borane here into our alcohol. So now for the actual oxidation step here. So first we have hydroxide ion from sodium hydroxide that's in there, comes and deprotonates our peroxide, and it forms this peroxide ion here, minus. And then what happens is this goes and attacks our boron, which gives us this ugly looking molecule next. And make sure I color code this. BH2, it's got a minus charge on it. Let me color code this oxygen. There's OH here. And then this undergoes a rearrangement, which isn't uncommon to see in stuff where you use peroxides, but this is how, it's kind of a weird one because it's hard to wrap your head around, but this is what happens here. So this bond here, there's a negative charge on it, comes in, moves this kicks off here, and he goes and he's a hydroxide ion now. And then what we have is this. Ooh, it's so hard to draw straight on the iPad sometimes. Where now our oxygen is bound to that carbon there. And we have BH2. Now, we need to turn that into an OH and get rid of that BH2. So what happens? That OH we had, he comes back, minus, and he attacks the boron, who then kicks its electrons up onto the oxygen. So there's a lot to keep track of, I know, guys. It's a tough mechanism, especially for organic one. Then we are left with an alkoxide. Ooh, I forgot to make it blue. And then, because this is in sodium hydroxide, aqueous, we're assuming that there's, water floating around. And if you remember in the various first step, we did make a water atom. So we're going to have our water here, and hydroxide is going to pluck that off. And we are finally left. Oh, I keep forgetting to make it blue. We're finally left with our molecule. All right, so I know that was a long, kind of drawn out mechanism, but even if you don't always remember the mechanism, what you need to remember is that when you have an alkene, hydroboration turns it into an alcohol, but it adds it at the least substituted position, or the less, giving you anti-Markovnikov addition, and then it adds sin. So we were going to make these wedges. This would be a wedge, and then the hydrogen that you added would also be a wedge because it's pushed on down from one face. So that's the big takeaway. Make sure you practice that mechanism if you're struggling with it, and that'll help you understand what the correct product is formed. Just remember, if you can't remember the mechanism, you're panicking in your exam. If you see this, just remember regiospecific, anti-Markovnikov addition, sin addition. If you can just remember that, you should do just fine, unless the question is draw the mechanism. But so, as always, if there's anything you're struggling with, you can DM it to me or comment it in the video below.